Aqueous equilibria, acids and bases, chapter 14. So we can talk about two definitions of acids and bases, the first one being the Arrhenius definition. And he talks about the fact that if you add an acid to water, we increase the amount of protons or hydronium ions. And when you put a base into water, we increase the concentration of hydroxide ions. So with Arrhenius, you have to have water present. The Bronsted-Lowry definition allows us to talk about other types of acids and bases. So an acid is a proton donor and a base is a proton acceptor. So really then all you need to be a Bronsted-Lowry acid is to have a hydrogen connected to an electronegative element, so it easily dissociates. And to be a base, you simply need to have a lone pair of electrons. So this shows hydrochloric acid reacting with water to produce the chloride ion and a hydronium ion. So the acid donated the proton to water. That's the Bronsted-Lowry definition. Or we can also look at the fact that we increased the amount of the hydronium ion present, which would be the Arrhenius definition. So any generic acid, whether this be a strong acid or in this case it's a weak acid because we see our equilibria arrows here, the acid will donate the proton to water. We will always make the hydronium ion, and then we end up with a conjugate base. So here's our acid, HA, similar to our A-, so acid conjugate base pair here. Water is a base on this side, and its conjugate acid is H3O+. So the conjugate base of an acid is simply what's left over once the proton has left. So we donate the proton, the hydrogen leaves its electron behind, which then the conjugate base most oftentimes is negative. Conjugate acid is just the opposite of that. So you start as a base, you've accepted a proton, and generally speaking, you are going to have a positive charge. Regardless, if you are the conjugate base, your charge will go down by 1. If you are a conjugate acid, your charge will have increased by 1. Notice here, water is neutral. It accepted the proton because it's a base, so its charge went up. The acid donated its proton, the charge went down. So water can act both as an acid and a base, which means that it is amphoteric, so it can both donate a proton or accept a proton. So at 25 degrees Celsius, we can write out an equilibrium expression for the auto-ionization of water. So water plus water gives us the hydronium ion and the hydroxide ion. Water is pure liquid. These substances are aqueous, which is why they are the only ones that show up in solution. And just keep in mind that throughout this chapter, we use the proton H+ interchangeably with the hydronium ion, H3O+. They mean the same thing. So no matter what the solution contains, the product of your protons times your hydroxide ions will always equal your equilibrium constant of 1 × 10⁻14. If you are in an acidic solution, your concentration of H+ will be much higher than your hydroxide, and just vice versa. If you are in a basic solution, then your hydroxide ion will have a higher concentration than your proton. So we can talk about acid strength. There's 2 types of acids. We have strong acids and we have weak acids. So if you are a strong acid, you have a very, very large Ka. Oftentimes these values aren't even listed because they're on a magnitude of 10 to the 30th. So strong acid means complete dissociation of the proton. Strong acids will yield a weak conjugate base. So that weak conjugate base has no power to pick that proton back up. On the contrary, we have weak acids, which have a very small Ka and lie effectively on the reactant side. So weak acids have Ka values 10 to the -4th and smaller. So the weaker the acid, the stronger its conjugate base. And just vice versa. So here's a picture showing the difference between strong acids versus weak acids. Here we have a strong acid. We start off with a certain concentration of HA. It has completely dissociated into H pluses and A minuses. So whatever your concentration is here that you start with, you end up with the same concentration of protons and conjugate base. However, if we have a weak acid, HB, it only dissociates to a very small extent. So notice here we have most of our HB left over, only producing very small amounts of our proton and our conjugate base. So here's a couple different ways just to look at the differences between strong acids and weak acids. First of all, we can compare the Ka values. Ka for strong acids tend towards the product side. Ka for weak acids tend towards the reactant side. So where does the equilibrium lie? Far to the right if you're a strong acid, far to the left if you're a weak acid. When we look at the equilibrium concentration of your protons versus your initial acid, these are effectively equal for a strong acid. For a weak acid, your amount of protons that have dissociated is much, much smaller than your initial concentration of that acid. And in terms of strength of your conjugate bases, your conjugate base here is a much weaker base than water, which really just means that if anything else would react in solution, it would be water, not the A minus, not your conjugate base. Here, your weak acid has the potential, its conjugate base has the potential to react in its own way because it is a much stronger base than water. So we can still see reactions with the conjugate base of these weak acids. And that'll lead us into next chapter when we talk about buffer solutions. So how do we measure the acidity or basicity of something? We use the pH scale. And the pH just means power of the proton. What is the amount of protons that we have in the solution? The more that we have, the lower the pH. So pH equals negative log of your H plus. Anytime you put a little p in front of something, you're going to take the negative log. That is what that means mathematically. So we'll see that we can take pKb's, pKa's. It just means take the negative log of whatever it is that you're interested in. So it's a much easier way to represent the acidity of a solution. Instead of saying, I have a concentration of 2.3 times 10 to the negative 7 molar hydronium ion. What does that mean? It doesn't mean a whole lot. But if I can say, hey, I have a pH of about 6.8, that tells us a lot more. So our pH decreases as your H plus increases. And this is because your exponents for your concentrations are negative, and we're taking the negative log of that particular substance. In terms of significant figures, the number of decimal places in the log is equal to the number of significant figures in the original number. What does that mean? So if I have 3.4 times 10 to the negative 5th, I have 3.4, that's 2 significant figures in a concentration. When I take the negative log of that, I will then have 2 significant places past the decimal point. So generally, we are going to represent our pHs with a total of 3 significant figures, effectively, like 1.75, 4.39. But when we get into bases, we would have 10.13 or 11.76. So we're always going 2 places past the decimal point. There's 3 possible situations when talking about pH, and that is we have a neutral solution if your hydroxide ion concentration is equal to your proton concentration. If your protons are more than your hydroxides, then we have an acidic solution. And if your protons are less than your hydroxides, then you have a basic solution. So here's just a general picture to show the pH ranges of some common items. So 1 molar sodium hydroxide, this is a strong base. It is a soluble metal hydroxide. Group 1 metals are all strong bases. Ammonia, so what you use in your Windex, that has a pH of 12. Blood is slightly basic, around a pH of 7.4. Pure water, pH of 7, completely neutral. Milk is slightly acidic. Then you have vinegar, which is acetic acid, pH of 3. Your lemon juice is about 2.5. Stomach acid has a pH of 2. And a strong acid, such as 1 molar hydrochloric acid, is just a little bit above 0. So once again, your pH, when it is 7, you're neutral. If it's greater than 7, it's basic. And if it's less than 7, it's acidic. So low pHs mean you're in the acidic range. High pHs mean that you are in a basic range. So we've talked about pH. What is POH? Well, POH simply means take the negative log of your hydroxide ion concentration. So if we do a little bit of math here, if we take the negative log of everything that's present, we can see that we have pKw, right? Take the negative log, just means put a little p in front of it. pKw equals pH plus POH. If we actually take the negative log of your value of Kw, which is 1 times 10 to the negative 14, we see that if you add the pH and the POH, it adds up to 14. Now, the POH scale is just the opposite of the pH scale, which means that a low POH would mean you're basic, and a high POH would mean that you're acidic. 7 is still neutral. So how do we solve weak acid equilibrium problems? This is what we are going to do when we start setting up ice tables. So first thing we want to look at is what are the major species in the solution that are actually going to contribute to the pH? So we're looking at your weak acid and writing a balanced equation for how does that weak acid react with water. So it's always going to be acid plus water yields hydronium ion conjugate base. So you have to use the value of your equilibrium constant, set up your equilibrium expression. In doing so, then we are able to look at an initial concentration of your weak acid, and then we can solve for your equilibrium concentrations by setting up your ice table. So defining that change, we have an initial concentration I, your C is for change, which we define as X. So we're subtracting X's from the reactant side, adding X's to the product side, and keeping in mind that water is one of our reactants, but it is a pure liquid, so it does not come into play. So when we write our equilibrium concentrations in terms of X, it'll be initial concentration minus X for your weak acid, and then X for your hydronium ion, and X for your conjugate base. So we'll substitute those equilibrium concentrations into the equilibrium expression, and then we'll solve for X, the easy way. So that is when we assume that your X here is 0, basically. That our HA concentration is not going to change very much because your Ka values tell you that this reaction lies on the reactant side. So we expect for this to remain effectively constant. And you can see if the approximation is valid by using the 5% rule. So this is looking at, is the change in X within 5% of your initial concentration when you do that subtraction? Is it within 5%? So when you have calculated X, you have effectively calculated the concentration of your H plus or your hydronium ion. Once you know that, you take the negative log, and then you have the pH. From that, you can not only find your POH, but you can also find the amount of hydroxide ion present and the amount of your conjugate base as well. So instead of using Ka values, we can also simply talk about percent dissociation or percent ionization. And these are related to each other. So your percent dissociation looks at how much is dissociated out of your initial amount that you start with, times 100%. So percents always are some type of ratio, part of it over the whole, times 100%. So for a given weak acid, the percent dissociation increases as the acid becomes more dilute. Polyprotic acids. Poly means more than one. Protic, we're talking about protons. So these particular types of acids have more than one proton to donate to a solution. But polyprotic acids will only donate their protons one at a time. So the conjugate base of the first dissociation, whatever that is, becomes the acid in the second step. And then if you've got another proton to donate, that conjugate base would become the reactant in the third step. So for typical weak polyprotic acids, in terms of your dissociation, or sorry, not dissociation constants, your equilibrium constants, Ka1 is the dissociation for your first proton, Ka2 is for the second, Ka3 would be for the third. So your equilibrium constant for your first proton is much larger than what it is for your third proton. And hopefully this makes sense, because once we get into Ka2, Ka3, we can actually look at the fact that now both of these can behave as acids or bases. And generally speaking, they will prefer one way or the other. And that's based on Ka values or Kb values. And within these, usually the first dissociation step is the only one that's really going to be important to the pH, because as you keep dissociating the next proton, the next proton, the next proton, very, very, very little amount of hydronium ions will be created in those successive dissociations. So we've talked about weak acids. Now let's look at weak bases. So we can use the equilibrium expression for a weak base, and we use Kb as our equilibrium constant. Your pH calculations are very similar to how we set up our tables for weak acids. So you're going to do an ICE table, starting with initial concentrations of your weak base. And one of your products then is the hydroxide ion, and your other product is your conjugate acid. So now when you set up your ICE table, when you're solving for X, you will actually be solving for your hydroxide ion concentration. But there is a relationship between hydroxide and hydronium. So you can either calculate the pOH and subtract from 14 to get the pH, or you can use the equilibrium expression for water and solve for the hydronium ion concentration, and then take the negative log of that to get to the pH. So there's two ways that we can find pH when looking at weak bases. Now, usually our weak bases are amines, and that is just a derivative of ammonia, which is NH3. So amine is an organic compound where now we have hydrocarbon chains attached to a nitrogen. And as I was just saying, we can calculate pOH and find the pH this way. Acid-base properties of salts. So a salt is an ionic compound. Generally, those are the compounds that are formed from an acid-base reaction. That, by definition, a neutralization reaction produces water and salt. So ionic compounds means that we have to have something positively charged, something negatively charged. So when these salts are put into water, they break up into ions, which can behave as acids or bases, or neither. So when we're looking at the reaction of a strong acid and a strong base, it will give a neutral solution. So in trying to figure out whether salts are acidic, basic, or neutral, we're actually going to be looking at what are the ions that are present. If you are a group 1 metal, an alkali metal, you cannot act as an acid in solution. If you were the anion that came from a strong acid, chlorine, bromine, iodine, nitrate, the perchlorate or chlorate ions, any of these are not going to be able to participate in reacting with water to create a pH. A basic solution will be formed if the anion of the salt is the conjugate base of a weak acid. So this means we're going to react a weak acid with a strong base. So hopefully this should make sense. Weak plus strong. Well, my base can completely dissociate because it's a strong base, and my acid can only partially dissociate because it's a weak acid. I hope I said that right. Oh, the weak acid can only dissociate a small amount. So we have an uneven balance there. For example, once again, in looking at whether a solution is going to be basic, we're concerning ourselves with what can the anion do, not what can the cation do. Cations have the potential to be acids in solution. Anions have the possibility of being a base. So once again, group 1 metals we ignore. We just cross those off. F. This came from HF, a weak acid, hydrofluoric acid. Here we have the acetate ion, which came from acetic acid, which is a weak acid. So in both of these instances, F- can react with water to produce hydroxide ions and HF. The acetate ion can react with water to produce hydroxide ions and acetic acid. So in this instance, then when we want to calculate pHs, we're going to just set up a ice table. So we can use the information that Kw equals Ka times Kb. So we would look at the fact that we have HF. This is how this started out, as hydrofluoric acid. And we will use the Ka value for HF to solve for the Kb. Then it's an equilibrium expression, ice table, solve for OH-, calculate POH, find your pH. Now, if we're going to have an acidic solution when we dissolve a salt into water, it is coming from the cation that is present. So for example, here we have NH4 plus, we have Cl-. Your chloride anion came from hydrochloric acid, which is a strong acid, which means that its conjugate base, here, the chloride ion, has no power to react with water to change the pH. However, the ammonium ion came from ammonia, which is a weak base. So then that allows the NH4 plus to act as an acid in solution and therefore decrease the pH. So once again, you would look for the Kb of ammonia because that is where this came from, solve for Ka, and then set up an ice table using your concentration of your ammonium ion. Solve for your equilibrium concentration of hydronium ion and take the negative log of that to get to the pH. So once again, this can be a little confusing, but with salts, if you have strong acid plus strong base, and this is one of the things why I say you have to memorize what those are, then your salt is neutral. If you have a strong base that is reacted with a weak acid and you end up with a salt, that salt will be basic. If you have a strong acid that is reacted with a weak base to form a salt, then that salt will be acidic. So you're asking yourself, where did these ions come from? This ion came from sodium hydroxide because your cation comes from your base. Where did this ion come from? It came from an acid, HF. So this is what you're asking yourself. Where did these ions come from? A strong acid or a strong base, or a weak acid or a weak base. It's the only way that we can really identify how salts will behave in solution. So, and as I mentioned earlier, you use Ka when you're starting with an acid. This is always true. Kas are for acids, Kbs are for bases. So if you're setting up an equilibrium reaction, you have to make sure you know what you're starting with. Is it an acid or is it a base? So here's a table of what I just talked about. Sodium chloride is a neutral salt because this came from sodium hydroxide. This came from hydrochloric acid. Strong plus strong gives you a neutral salt. Sodium fluoride, this came from sodium hydroxide. This came from hydrofluoric acid. Strong base, weak acid gives you a basic solution because the fluoride ion can react with water to produce hydroxide ions. An acidic salt would come from the ammonium ion, which came from a weak base. Chloride ion came from a strong acid, so this cannot react with water, but this can. So we would use a Ka, calculate H+, and see that we have an acidic solution. Now, what happens when we have both a base, a conjugate base of a weak acid, and a metal? Any type of metals, especially metals with higher charges, can act as acids in solution. That's a Lewis definition, which we'll talk about in a minute. So in that instance, we have to look at both Ka and Kb values for our respective conjugates here and see which one would win. Whichever one is bigger, that is the one that would predominate in solution. So switching gears and just talking about some of the things that affect acids and bases and their strengths. So when we look at binary compounds, which simply means protons and only one other nonmetal that is present, HF, HCl, HBr, HI, H2O, H2S, H3AS. So we're only looking at there's two elements present, hydrogen and one other element. So we're not looking at what we call oxoacids. So bond polarity. If you have a very polar bond, then that is good because that means that the electronegative element already has pulled hydrogen's electron towards it, which means that it makes it much easier for the proton to just leave. However, if we're looking at bond strength, we want to have a low bond enthalpy or bond strength because that tells us what is the energy that is holding these two atoms together. So if you have high polarity and low bond enthalpy, the likelihood of your acid being strong is very good. So here we can see bond strength decreasing as we go down the group 7, as we go down the halogens, and this is because the size of these respective ions gets bigger and bigger, which means it's much harder for hydrogen's 1s orbital to overlap with the respective s orbitals, or I should say p orbitals, on these elements. Now, electronegativity-wise, this is actually the most polar bond. However, we see that HF is a weak acid, and this is simply because the bond strength is so much greater. So the bond strength wins over the polarity. The rest of the acids that are from halogens are strong acids. So now we can look at oxyacids, and that means that we have oxygens present along with an electronegative atom. So the more oxygens that you have, the stronger the acid that you are. So here, very large value for perchloric acid. Ka here is approximately 1, so it kind of can be considered a strong acid, but generally speaking, I would not consider it a strong acid. And now we see that we're times 10 to the negative 2 times 10 to the negative 8. So these two are really kind of in the middle, this one clearly being more products than what this one would be. We can look at H2SO4 versus H2SO3. Sulfuric acid has a very large Ka, meaning the first proton dissociates readily. With HSO3, or sulfurous acid, we see a Ka that is smaller. So more oxygen means I'm a stronger acid. Nitric acid versus nitrous acid. Very large value here, so this proton goes away completely. And now we see a Ka value of times 10 to the negative 4th, which means that most often this proton stays attached to the oxygen. So acid strength. When you're looking at oxyacids, it's the more oxygens you have, the stronger you are. So what if you're an oxyacid and we want to look at bond polarity? So comparing Cl to Br to I and then to what we call a methyl group. So the electronegativity is clearly decreasing as we go down our group of halogens, and then for carbon, because the oxygen is connected to carbon here. In terms of your acid strength, we can see that the more electronegative your atom is that is connected to the oxygen, the stronger your acid will be. So we decrease our Ka values, meaning weaker, weaker, weaker acid, because our bond polarity of these atoms has gone down due to the decrease in the electronegativity. So acid-base properties of oxides. What happens when we have a metal oxide versus a non-metal oxide? So acidic oxides or acid anhydrides, we're looking at covalent bonds, which means X needs to be a non-metal, and we have a very strong bond between these two elements. So for example, sulfur dioxide, nitrogen dioxide, carbon dioxide, we can dissolve these into water, and each of these will produce an acid. So we have sulfur. There's an electronegativity difference between our central atom and our oxygens. So this bond, what this is saying here is when we're dissolving these bonds stay intact, and then the hydrogen atom will actually bond to one of the oxygens. And then that is what is really forming the acid, because the protons are never directly bonded to these highly electronegative elements. When we're looking at oxides, we're looking at oxyacids here, different than just your binary acids. So basic oxides or basic anhydrides, you're looking at an ionic bond. So potassium oxide, calcium oxide, sodium oxide, etc. So we're looking at group 1, group 2 metals. We can also look at transition metals that can form bases. They're just not very soluble. So what we're looking at is we want a low electronegativity with this OX bond. So it's ionic. It's subject to be broken apart in polar water, which can then produce a basic solution. And the oxygen then will actually hook up with a proton. So last definition of acids and bases, we can look at a Lewis acid, which is now an electron pair acceptor, versus a base, which is an electron pair donor. So for example, here, aluminum with a +3 charge, positive, which means that it can attract lone pairs of electrons on, say, a water. So this is a hydrated aluminum complex. Aluminum then is acting as an acid. Water is acting as a base. Electron pair acceptor, electron pair donor. We also can look at electron deficient elements like boron. Boron makes a really good Lewis acid. It only starts with 3 electrons, so it can only share those, which means generally it only has 6, leaving it unstable because it really wants to have 8. So boron can act as a Lewis acid because it's missing a pair of electrons. Ammonia acts as a Lewis base. Why? Because nitrogen has this lone pair of electrons to donate. So we've also talked about ammonia is a base under the Bronsted-Lowry definition. Why? Because at the same time that nitrogen can donate a pair of electrons, it can also accept a proton because of this lone pair of electrons. So now we formed this complex between boron trifluoride and ammonia. So Lewis acids, Lewis bases. Most common Lewis acids are going to be metals with high positive charges, iron 3+, aluminum 3+, etc. Your Lewis bases are going to be anything that has a lone pair of electrons to donate to the acid. And notice here, when we're reacting Lewis acids and Lewis bases, we don't necessarily end up with a conjugate acid, conjugate base situation. We're oftentimes forming completely new structures when doing Lewis acid base chemistry. So just to review our three models for acids and bases, we have Arrhenius, which says we increase the protons in solution if we're an acid, we increase the hydroxide ions in solution if we're a base. Bronsted-Lowry says I'm a proton donor if I'm an acid, or I'm a proton acceptor if I'm a base. And then Lewis says I'm an electron pair acceptor if I'm an acid, I'm an electron pair donor if I'm a base. So with these three definitions, we are able to cover all of the chemistry that happens and explain why we see solutions as acidic or basic. Because Arrhenius limits us to only being in water. Bronsted-Lowry limits us in the fact that we have to have protons present. But Lewis just says, hey, all we care about is electron pairs. And that means that we are all-inclusive in terms of our definitions. So within this chapter, we need to go over, or you need to understand the different definitions that we've talked about, understand the pH scale and the relationship between the hydronium ion and the hydroxide ion in solution. Most importantly, we're going to be focusing on doing those ice tables to calculate pHs of either weak acids or weak bases in solution. And then I want you guys to really focus on how do we determine whether a salt is acidic, basic, or neutral, because that seems to be quite confusing. And in doing that, I strongly, strongly, strongly suggest that you simply memorize your strong acids and strong bases so that you can just recognize those. We also talked about different things that affect acid strength, so bond polarity, bond strength. With oxyacids, the number of oxygen atoms increases your acidity, how strong you are. We also looked at what happens if we have metal oxides versus non-metal oxides. We dissolve those in water. Do we form bases or acids? And most importantly, though, I just want to emphasize how many ice tables you guys are going to have to do in this chapter to really understand this. And there's going to be ice tables in the next chapter. So you have got to get that under your belt. So good luck studying.